It was never supposed to happen like this. A spacecraft drifting more than 200,000 miles from Earth, costing billions, built by the most advanced engineers in human history, and inside it, a commander trained for every imaginable emergency, says something that no one ever expected to hear in orbit. There are two Microsoft Outlooks, and neither of them are working. That single sentence, spoken calmly in space just hours after launch, is not just a technical complaint. It is a signal that something deeper about our systems, our assumptions, and our technology is being tested far beyond what we prepared for. Most people laugh when they first hear it. A space mission failing at email feels almost absurd. But that reaction hides something important. Because this is not about email at all. It is about what happens when human systems, designed on Earth, are pushed into an environment that does not follow Earth's rules. It is about what breaks when complexity meets distance and when assumptions stop holding. To understand why this matters, we need to start with a simple idea that is often misunderstood. Software is not invisible. It is not just code sitting quietly in the background. Software is the control system of modern civilization. It runs spacecraft, hospitals, aircraft, power grids, and communication networks. When it works, we barely notice it, but when it fails, the impact is immediate and sometimes severe. History already gives us warnings about this. In 1999, NASA lost a Mars orbiter worth $125 million, not because of hardware failure, but because of a simple mismatch in units between two software systems. One team used metric, another used imperial, and the error silently destroyed a mission. Nothing dramatic happened in the moment. There was no explosion, no visible failure. Just a slow, invisible breakdown of communication between systems that were supposed to work together. A few years later, during the Space Shuttle Columbia disaster, the problem was different, but the pattern was familiar. Foam struck the shuttle during launch, damaging the heat shield. Engineers suspected the issue, but the software tools they had could not properly model the damage. The data was incomplete, the analysis uncertain, and the decision was made to continue the mission. 7 lives were lost, not because information was absent, but because the systems designed to interpret that information were not sufficient for the complexity of the situation. These events reveal a simple but uncomfortable truth. Software failures are not always dramatic. They are often quiet, hidden inside layers of assumptions, only becoming visible when it is too late. Now fast forward to Artemis II, a mission designed to take humans farther into space than they have gone in decades. Everything about it represents precision, planning, and control. And yet, within hours of launch, something unexpected happens. The crew attempts to use onboard communication systems, and Microsoft Outlook fails. Not once, but twice, on 2 separate instances running in the spacecraft environment. At first, this sounds almost trivial. Email in space should not be important compared to navigation, life support, or propulsion systems. But that reaction misses the point, because the issue is not the email itself. The issue is that a widely used, heavily tested piece of software failed in a completely new environment that it was never originally designed for. And that raises a deeper question. If something as standard as Outlook can fail in space, what does that say about the rest of the software stack running the spacecraft? The Orion capsule is not just a vehicle. It is a dense network of computers, processors, and interconnected systems. It depends on millions of lines of code working together perfectly. Navigation, timing, life support, communication, and control systems all interact continuously. Every layer depends on another layer behaving exactly as expected. But the problem is that expectations are based on Earth conditions, stable networks, predictable latency, and consistent infrastructure. Space does not provide any of those guarantees. So when something breaks, even something small, it is not just a bug. It is a warning that assumptions are being tested in ways we cannot fully simulate on the ground. And that is where this story really begins. Because this is not just about one software failure. It is about what happens when complexity leaves the environment it was designed for. And as we move deeper into space exploration, that question becomes more important than ever. In the next part, we will look at how spacecraft software actually works, why modern systems are far more complex than anything built during Apollo, and why that complexity is creating new risks that engineers are still struggling to fully understand. The moment we start looking beyond the surface of this Artemis II situation, something becomes clear that most people never think about. The issue is not that a single application failed in space. The real issue is what that failure reveals about how fragile modern systems become when they leave the environment they were built for. To understand this properly, we have to go back to what software actually is in a spacecraft. Most people still imagine a rocket or capsule as a mechanical machine with a few computers inside it, but that idea is outdated. Modern spacecraft are closer to flying data centers than traditional vehicles. Every critical function is controlled by layers of software that constantly communicate, calculate, and adjust in real time. Navigation is not just a pilot looking at controls, it is algorithms processing orbital data. Life support is not just oxygen tanks and filters, it is automated systems constantly monitoring pressure, temperature, and air quality. Even engine burns are managed by precise digital instructions that must execute at exact milliseconds. On top of this core system, there are secondary layers. These include communication tools, data interfaces, monitoring dashboards, and yes, even commercial applications like Microsoft Outlook. These are not directly responsible for keeping the crew alive, but they are still part of the operational environment. And this is where complexity begins to quietly build. Each system in a spacecraft is designed with assumptions. Those assumptions work perfectly on Earth. Engineers assume stable internet protocols, predictable system responses, and consistent operating conditions. But space does not follow those rules. Latency changes everything. Network structures behave differently. Timing shifts in ways that are hard to fully reproduce on Earth. When systems built on different assumptions are combined, small mismatches begin to appear. And these mismatches do not always show up immediately. They often appear only when the system is in actual use, under real mission conditions. This is what engineers call integration failure, not a single broken component, but a breakdown in how components interact. And this is where modern spacecraft become especially vulnerable, because unlike early missions, where systems were simple enough to fully understand, today's spacecraft rely on millions of lines of code developed by different teams, sometimes even different organizations. No single engineer fully understands the entire system anymore. Instead, the system is understood in parts. This shift has created a new kind of risk. To see how different this is, we can look back at Apollo-era computing. The Apollo guidance computer had extremely limited memory and processing power. But that limitation was actually an advantage in one sense. It forced simplicity. Engineers could review almost every line of code manually. They could fully understand how the system behaved in every scenario. Nothing was hidden in layers of abstraction. Modern spacecraft are the opposite. They depend on operating systems, external libraries, communication frameworks, and commercial software packages. Each layer adds capability, but also adds dependency. And every dependency is another potential point of failure. The key problem is not that these systems are poorly built. In fact, many of them are extremely reliable on Earth. Microsoft Outlook, for example, is used by hundreds of millions of people and has been tested across countless environments. But Earth environments and space environments are not the same thing. That difference matters more than it seems, Because in space, systems are isolated. They do not have the same network support infrastructure that they rely on back on Earth. Authentication systems behave differently. Communication timing changes. Even small delays or configuration differences can produce unexpected behavior in software that assumes a stable environment. So when Outlook failed aboard Artemis 2, it likely wasn't because Outlook is broken. It was because the environment it was placed in was fundamentally different from what it was designed to assume. And this leads to a deeper engineering truth. Modern systems do not fail because one thing is wrong. They fail because many small assumptions stop aligning at the same time. This is what makes space systems so difficult to design. Every additional layer of software increases capability, but also increases the number of possible interactions between systems. And those interactions are impossible to fully predict in advance. You can test thousands of scenarios on the ground. You can simulate extreme conditions, but you cannot simulate every combination of timing, load, network behavior, and system interaction that might occur in real flight conditions. And when something unexpected happens, it is often not the core systems that fail first. It is the secondary systems, the ones that were assumed to be stable because they work everywhere else. This is why the Artemis 2 incident is important. It shows that even non-critical systems can behave unpredictably when moved into space. And that raises a serious question for future missions. If small, familiar tools can behave unexpectedly, what happens when similar complexity exists in life-critical systems over longer missions, where there is no immediate support from Earth? In the next part, we will go deeper into what engineers call emergent failure, and why the most dangerous problems in modern spacecraft are not caused by individual bugs, but by interactions between systems that were never meant to work together in the first place. When engineers first saw the Artemis 2 Outlook issue, the instinct was to treat it as a simple technical glitch. Something minor, something routine, something that could be patched and moved past without much concern. But the deeper you look, the more that explanation starts to fall apart. Because what happened here is not just a single failure. It is a demonstration of how modern systems can break in ways that are not tied to one specific fault, but to the interaction of many correct parts behaving in an unexpected environment. This is where the concept of emergent failure becomes essential. Emergent failure is not caused by one broken component. Instead, it appears when multiple systems, each functioning exactly as designed, interact in ways that were never fully predicted. On their own, each system is reliable. Together, under certain conditions, they produce behavior that no individual engineer intended or anticipated. This idea is not limited to spacecraft. It exists in many complex systems. In financial markets, for example, individual trading algorithms can all follow risk-reducing rules, yet their combined behavior can trigger sudden market instability. In nature, simple rules followed by birds or fish create complex coordinated movement patterns that no single animal controls. The behavior emerges from interaction, not design. Spacecraft software is now entering the same territory. On Artemis 2, Outlook was not operating in isolation. It was running inside a highly specialized environment connected to spacecraft communication systems, authentication layers, and operating constraints that differ significantly from standard Earth-based systems. Each layer was designed independently, tested independently, and validated under expected conditions. But space removes those expectations. It changes timing. It alters network behavior. It introduces latency and isolation that most commercial software is not built to handle natively. When these differences stack together, they can create interaction effects that are extremely difficult to predict. And that is where emergent failure appears. Not as a crash, not as a dramatic shutdown, but as something subtle. A system behaves in a way that is technically unexpected, but not clearly broken. A function fails under a specific combination of conditions that no test on Earth ever reproduced exactly. This is what makes it so dangerous, because nothing looks obviously wrong until the system is already in use. In Artemis 2's case, the failure happened early in the mission. The crew was still adapting to the spacecraft environment, and ground control was actively monitoring systems, so the issue was identified and managed without escalating into something serious. But that outcome should not reduce its significance. If anything, it highlights how close modern missions are to the edge of complexity limits. Because here is the critical point. You cannot fully test emergent behavior in advance. You can simulate conditions, you can model interactions, but you cannot exhaustively simulate every possible combination of system states, timing differences, and environmental variables that occur in real spaceflight. The number of possible interactions grows exponentially with system complexity. Every new piece of software does not just add one new function. It adds multiple new interaction pathways with every existing system. Over time, this creates a web of dependencies that becomes increasingly difficult to fully understand. This is why modern spacecraft engineering has shifted focus away from trying to eliminate all failures and toward managing them. Instead of assuming perfection, engineers now assume that failures will occur. The goal is to design systems that can continue operating even when parts of the system behave unexpectedly. This includes redundancy, fallback systems, error isolation, and recovery protocols. But even those strategies have limits, because resilience still depends on understanding failure modes. And emergent failures, by definition, are not fully known in advance. They exist in the space between tested scenarios. This is why Artemis 2 matters beyond its immediate technical impact. It is not just a story about an email system in space. It is a real-world example of how complexity creates blind spots in even the most advanced engineering environments. And it raises an uncomfortable question. If a non-critical system like Outlook can fail under these conditions, what does that imply about the behavior of more critical systems when missions become longer, more distant, and less supported by real-time communication with Earth? As we move forward, spacecraft will operate farther from home, with longer communication delays and less immediate human oversight. That means systems will need to function not just correctly, but independently. They will need to detect their own failures, adjust their own behavior, and maintain stability without external intervention. In the next part, we will explore how engineers are trying to build exactly that kind of software systems that can survive uncertainty, adapt to unexpected conditions, and continue operating even when human support is no longer instantly available. At this stage, the Artemis 2 incident stops being just a curious software glitch and starts becoming something far more important, a preview of the kind of problems future space missions will face on a much larger scale. Because once you accept that emergent failures can happen, the real question becomes not how to eliminate them completely, but how to survive them when they inevitably appear. This is where modern spacecraft design is undergoing a quiet but major shift in philosophy. For decades, space engineering focused on prevention. The goal was simple: design systems so reliable that failure would be extremely unlikely. Every component was tested, verified, and validated under strict conditions. If something could go wrong, engineers tried to eliminate it before launch. But as systems became more complex, that approach started to reach its limits. The reason is simple: you cannot fully test what you cannot fully predict. And in a system made of millions of interacting parts, prediction becomes incomplete by nature. There are just too many combinations, too many variables, and too many hidden dependencies between systems that were built separately. So, engineers started to change the goal. Instead of aiming for perfect reliability, they began focusing on resilience. Resilience does not mean a system never fails. It means the system can continue operating even when something does fail. It means isolating problems, limiting their impact, and keeping the core mission alive even under unexpected conditions. This is a crucial distinction, especially for spacecraft. Because in space, there is no quick repair crew. There is no immediate hardware replacement. There is no instant technical support. Everything must be handled either by onboard systems or through delayed communication with Earth. And that delay becomes more critical as missions move farther away. On a mission to the Moon, communication delays are short enough that ground control can quickly diagnose and fix most issues. But as we look toward Mars and beyond, those delays stretch into minutes or even hours. In that environment, a system cannot afford to wait for instructions. It must be capable of responding on its own. This is why autonomous software is becoming one of the most important areas of aerospace research. The idea is to create systems that can monitor their own behavior in real time, detect when something is not functioning as expected, and take corrective action without waiting for human input. These systems would not just follow instructions. They would interpret conditions, recognize anomalies, and adjust their own configuration to maintain stability. In theory, this would dramatically reduce the risk posed by unexpected failures. But in practice, it introduces new challenges. Because autonomy means giving software the ability to make decisions. And decision-making systems must be carefully constrained. If an autonomous system misinterprets a situation or applies the wrong correction, it could potentially make a small problem worse instead of better. So engineers face a delicate balance. Systems must be intelligent enough to handle uncertainty, but controlled enough to remain predictable. This tension defines the next generation of spacecraft design, and it is exactly the kind of problem the Artemis II Outlook failure helps illustrate. While Outlook itself is not a critical system, its failure highlights how even widely used, heavily tested software can behave unexpectedly when placed in unfamiliar conditions. That insight is important because it shows that reliability on Earth does not automatically translate to reliability in space. This is a point that is often underestimated. On Earth, software operates within a large supporting infrastructure. There are backup servers, redundant networks, constant connectivity, and rapid update cycles. If something fails, it can often be corrected quickly without major consequences. In space, none of that exists in the same way. The spacecraft is isolated. It must rely on preloaded software, limited connectivity, and carefully timed communication windows. Every system must function correctly within those constraints, without assuming help is immediately available. This is why even small failures matter more than they seem. They reveal how systems behave when stripped of their supporting environment, and that behavior is not always predictable based on Earth-based testing. So when engineers saw Outlook fail aboard Artemis II, they did not just see a minor inconvenience. They saw evidence of a deeper issue, that commercial software, even when highly reliable on Earth, may behave differently in space when removed from its expected infrastructure. And that realization feeds directly into future design decisions. Because as missions become longer and more distant, engineers will need to decide carefully which systems can safely be brought into space environments and which must be rebuilt from the ground up for reliability in isolation. This is no longer just a software question. It is a systems design question, a mission planning question, and ultimately a question about how humans extend their technological civilization beyond Earth. In the next and final part, we will bring everything together and explore what this means for the future of space exploration and why this small email failure may actually represent a much larger turning point in how we design technology for the universe beyond our planet. At this point, the Artemis II Outlook incident is no longer just a story about software misbehavior in space. It has become a lens through which we can understand a much larger problem, the growing gap between the complexity of the systems we build and our ability to fully predict how they behave outside Earth. Because when you step back and look at modern spacecraft, a clear pattern emerges. These are no longer simple machines built around a single purpose. They are layered ecosystems of software, hardware, and communication systems, all tightly connected and constantly interacting. And the more these systems evolve, the more invisible dependencies they accumulate. Each layer brings power, but also hidden assumptions. A communication tool assumes a stable network. An operating system assumes predictable timing. A cloud-based service assumes constant connectivity. On Earth, those assumptions are safe because the infrastructure supports them. But in space, that infrastructure changes or disappears entirely. And when assumptions no longer match reality, even reliable systems can behave in unexpected ways. This is why integration has become one of the most difficult challenges in aerospace engineering today. It is no longer enough to build components that work correctly in isolation. Every system must also be tested in combination with every other system it might interact with. But here is the problem. The number of possible interactions grows far faster than our ability to test them. With every new layer of software, the system becomes more capable, but also more complex. And complexity does not grow linearly, it grows exponentially. That means even a small addition can introduce thousands of new potential interaction pathways that were never explicitly designed or tested. This is where unpredictability enters the system. Because no matter how carefully engineers design and simulate, there will always be combinations of conditions that were never observed before, and space is where those unseen combinations eventually appear. The Artemis II Outlook issue likely came from one of those rare intersections. Not a catastrophic failure, but a subtle mismatch between software expectations and the actual environment inside the spacecraft. A difference in timing, authentication, or network behavior that Earth-based systems do not normally experience in the same way. On its own, that might not seem significant, but in complex systems, small mismatches can reveal deeper structural issues. This is why engineers are increasingly shifting their thinking. Instead of assuming that all failures can be prevented, they now assume that some level of failure is unavoidable. The focus is no longer on eliminating every possible problem, but on building systems that can continue functioning even when unexpected problems occur. This is where the concept of graceful degradation becomes important. A resilient system does not collapse when something goes wrong. It reduces functionality in a controlled way. It isolates the issue. It preserves core operations while secondary functions fail safely. In other words, it prioritizes survival of the mission over perfect performance. This approach is already shaping the future of spacecraft design. But it also leads to a deeper realization. As systems become more complex, even resilience is not enough unless it is paired with autonomy. Because in deep space, there will be times when Earth cannot respond quickly enough to assist. Communication delays alone make real-time support impossible beyond a certain distance. So future spacecraft will need to manage themselves. That means onboard systems that can detect anomalies, analyze their own behavior, and take corrective actions without waiting for instructions. It means software that can distinguish between critical and non-critical failures and decide how to respond based on mission priorities. This is one of the most difficult engineering problems of our time.